For the first talk in the afternoon, we have again Christian telling us everything about pidfds. Welcome, Christian.
So I think I gave a talk about this in 2019, so it would be kind of interesting to contrast this, what I talked about back then, and compare it with now. So this is just an update of what we've been up to. I think, I don't know how many people actually follow it that closely. I know systemd people usually are the first ones to make use of the feature, so they're probably aware. So one brief introduction. Well, how many people know what a pidfd is? Oh, that's good. That's better than in previous years for sure. It's a file descriptor for processes, so it's pretty self-explanatory. They have been around for a while. I looked it up. The first basic concept of this was implemented in 5.1, and they're a stable handle for a process. That's essentially just all that they are, because we always had problems with PID recycling. Especially for a long time, we had a fairly low limit on Linux, so it was very easy to quickly recycle a process. For example, I mentioned this in the Quadam talk earlier. When you have a suid binary crashing, you can sick kill that suid binary, the one that started the suid binary, and then recycle the PID and trick the Quadam handler into operating on a different process than it originally intended. And if you have a pidfd, that can't actually happen because it will always refer to the same process. So if that process has died and the PID has been recycled, you send a signal through the pidfd, you get esarch, which is kernel speak for no such process. So it provides a very reliable way of interacting with processes. It's obviously not the first implementation of this. It's a concept that in similar form has been around for a longer time on FreeBSD, although the Linux implementation is slightly different, and by now, I don't know if you can say more comprehensive. It depends on what the original authors of I guess it's called procfd in FreeBSD intended. But for example, we also have pidfd open, which allows you to create pidfds for existing processes, which FreeBSD doesn't allow you to do. I think they had a comment in the man page about whether or not they want to support this. Yeah, so that's all that it is. So we're gonna go over a bunch of stuff. First of all, pidfs, get to that in a second. X address, exit information, reaped processes, SCM pidfd and SO peer pidfd, how you derive namespace file descriptors, pidfd thread, pidfd get info, globally unique inode numbers, and one of the recent additions was also exhaustive file handles. So let's jump right into it. The first one is inode numbering and pidfs. So the original, you can ask questions anytime you want, by the way. So the original implementation of pidfd was based on a concept in the kernel that is called anonymous inodes. So obviously Linux has this concept of everything as a file, and that is sometimes quite useful. And there are a lot of interfaces that don't really require a full-blown inode and file. They just require a handle that works like a file or behaves like a file. And that's what the anonymous inode infrastructure is for. It's basically a single inode that is shared across all users that just need an entry point into the kernel to interact with something like a file, and then you can have different file operations on top of it. So for example, if you have BPF maps or BPF file descriptors, IO-Uring file descriptors for an IO-Uring instance, and all that stuff, mount file descriptors, that's all based on the anonymous inode infrastructure. And pidfds used to be like that as well. That was very limiting because it meant like every pidfd used the same underlying inode, which is a problem, because if you want to have per instance inode information for a pidfd, so let's say you want to store additional information about associated with a pidfd, you need a separate inode in the kernel. It's just the way how it works, and we couldn't do this at all because like we reuse the same inode for every pidfd. So at some point I was like, okay, let's clean this up, let's implement a proper solution to this. We implement a tiny in-kernel file system. You know, I'm one of the file system maintainers, so everything is a file system to me. I'm just joking, but the idea was like use a minimal file system implementation for pidfds so that we can do whatever we want, essentially extend it however we want, and get away from this single inode problem. So one of the first things that we do that people wanted for a long time is implemented unique inode numbers. So I know that doesn't sound like a big deal, but it's basically like a unique identifier for each process that you didn't have before that we have now. It's exposed via the inode number, so you can get it from stat. And the nice thing is, because of how pidfds originally worked, this works consistent on 32-bit and on 64-bit, which is kind of cool, I think. The other thing is that each... so a pidfd, the kernel essentially always had a concept of a unique handle to a task, and that is struct pid. It's a bit more complicated because the kernel has struct task struct. That's an actual individual task, and then it has struct pid, which has linkage with certain task struct. We can go into detail. I don't think we necessarily need to, but suffice it to say, if you wanted to implement a pidfd that refers to a specific process, you could do it in two ways. You could either pin struct task struct, or you could pin struct pid. We don't pin struct task struct because that's a large amount of memory and comes with other drawbacks. So we always pin a struct pid, and a struct pid is just a stable handle on a process. Think about it like this. And so each struct pid with pidfs corresponds to a different inode, and so if you have to have the same struct pid, you have the exact same inode. That doesn't sound like a lot, but it's a pretty nice property if you want to compare processes with each other. Anyway, we have globally unique inode numbers now, which means it's fairly trivial to compare two processes to each other. You just stat them and compare the inode numbers. It's a bit more involved on 32-bit because the inode numbers can be only 32 bits wide, so we split the inode number between the inode number field and the iGeneration number. And if you use them, you can use them for the upper and lower bits, and you also get a 64-bit identifier, but that's most of the time that shouldn't really interest you unless you're really on 32-bit and you somehow have a use case for using and comparing pidfds. I don't know how common this actually is, but there is a long explanation of how that actually works. And if I get around to it, I should actually write a man page. I mean, we have a man page, I just haven't gotten around to filling it all of that info. So anyway, you could just use that, for example, instead of using a pidfd, you could also use the inode number of a process to refer to it in whatever form you want. Based on that, and that I think is pretty cool, we implemented pidfd file handles. So I think there was a talk before where this was mentioned. File handles provide a handle to a node without keeping a file open. So essentially, what does that mean? Usually, when you interact with a file, you have to open it, and then you have an FD, and that FD is private to you. It can be inherited across fork, but when you close it, the reference to that file is gone. Linux has an additional concept called a file handle, which is also supposed to be globally unique, but it's not completely true. It's usually only unique within a specific file system instance. So, for example, I could use the name to handle that system call, name a specific file in a Btrfs instance, gives me a file handle which encodes that specific inode, and then later I can use the open by handle at system call to open that file again technically without doing any path lookup operations. If you have captag read search, which is like saying, I don't really care about path version checks. I have the privilege to open that file. You can open any file on your file system, which is usually a problem, especially for privileged containers, because it means if you have file handles and you allow open by handle and you have captag research in the container, the whole world is wide open to you. You can open any file on the system if you wanted to. So usually it's blocked. But some file descriptors are more special than others. And so pidfds, we don't care about paths. There is no path lookup involved with pidfds. We either create them from from clone or via pidfd open. And the nice thing is you can now use name to handle that, and it will encode a pidfd, which means, for example, if you had a PID file where you stored a specific PID in it, you could now just store a file handle in there, and it would work, and it would be safe against recycling. So even if you wait for 3 months, all of your process crashes, and you try to reopen the same process again, it will fail if that process doesn't exist anymore. They can't be recycled. And I think that's a pretty neat property. Yeah. And it's guaranteed to be stable. So we guarantee this to be UAPI. So all you need to construct pidfs file handles is 64-bit inode number of the pidfd, and then you can create file handles for that and use them to interact with processes. The thing is, you don't pin any resources, right? You don't have to keep anything open. You just have a handle that you can get to whenever you want to get to it. We derive namespace file descriptors. So everything is a file descriptor, so a namespace file descriptors. Usually how you get at namespace file descriptors is you have to take the detour through proc, pid, ns, and then the various namespace links that you have to get to. That's the only way you can get it, could traditionally get at namespace file descriptors, and it always felt kind of limiting. Some long time ago, I already made it possible to use pidfds to change namespaces instead of namespace file descriptors themselves. So setns works with pidfds. You can say, for example, bring me into the namespaces of this specific pidfd, instead of having to first use the namespace file descriptors and then pass them to setns. And this is sort of the other part of the other side of the coin, where you now can use ioctls to derive the namespace file descriptors from the pidfd, as long as you have ptrace access rights to the process, which is essentially equivalent to the proc pid NS way of doing things. So that takes procfs totally out of the mix. You can just interact with namespaces purely based on identifiers, which is also pretty nice. pidfd get info, that was done by this guy at the front here, which is like usually the only way to get information about processes is, or mostly is, if you read procfs, and there was some desire to have a limited set of that functionality available just by interacting with the pidfd, and this is what we do nowadays. So you can get meta information about the process that a pidfd refers to, like, for example, its PID number, its credentials, its C group ID, exit information. We'll get to that in a second. Nowadays, also core dump information. Yeah, you can see what type of information is available on the right side. That is the UAPI header for this particular struct. It's extensible, so technically we could put a lot more stuff in there. But it becomes a sort of discussion whether or not you probably don't want to mirror everything that proc does in struct pidfd info, because like proc is a huge dumping ground, and I have no interest in duplicating that. pidfd info exit, that one I kind of really liked. So we usually when you close when you hold a pidfd and you close it, then the kernel doesn't pin any additional information. And we've now changed that, and one of the reasons why we did this is like this exit information concept. So what does it mean? When you usually have a process like a PID, if you're the father, you can reap it, and then you can read the exit information once. Unless you store it somewhere in Userspace, you can't retrieve it again. Once the process has been reaped, it's gone. You can't get at the exit status again. And if you're not the father, you could probably, if you have ptrace rights, you could do some ptrace dance to get the exit information of the process, but yeah, it's all pretty complicated. So what we did is we now store exit information in the pidfd itself, which means as long as you have the pidfd open, get to that in a second. You can read the exit information as much as you want from the process. Like pidfds are pollable. I haven't mentioned this, but you can stuff them into an epoll loop or IO-uring or whatever event loop, and then get notified about exit information, about exit, and when the process gets reaped. And you can read the exit status as many times as you want from the pidfd now, which is pretty useful. Like you can get the information, obviously, if the process has been killed or signaled or whatever. On the right is always a bit of code how this is implemented in the kernel. This is like the exit code path. There's a lot of intricate dances that we have to do to actually make this work. But this is nice because it also means even if the task is gone, like everything is gone, the task struct is gone, there's nothing there anymore in the kernel, you have the minimal amount of information about the process exit information. I mean, technically we could stash a lot more information in there, but exit information is the most useful. It's, for example, say, the classic problem, systemd journald gets notified about a process exit, and it gets a pidfd for that. It gets a pidfd for that process, but by the time it gets around to it, to actually process it, the other side is already gone and has been reaped, which means systemd has no idea like what exit information, what happened to the process on the other side. You could just read this off the pidfd now. That one's pretty cool. SO peer pidfd and SCMP pidfd that also ties into the Quadam story I mentioned earlier. It's essentially AF Unix socket have a way for the receiving side to retrieve the credentials of the the process that called connect, or that's SO peer pidfd, or you can get the credentials of the sender of a specific message, and that is SEM PID. And we mirrored these concepts to now work on pidfds as well, which means you can use the SO peer pidfd call to get a pidfd on the the process that called connect, or get a pidfd for the sender of a specific message, which essentially makes it possible to very securely authenticate clients. And there's another interesting feature here that I want to touch upon. Okay, let me fit this into here then. So, a constant problem has been once a task has gone, especially with AF Unix sockets. Like, for example, you could have a task called connect. That task immediately exits, and then something else sends messages via that AF Unix connection, right? And you have, if you try to get a pidfd onto that from that task via SO peer pidfd, the kernel would just tell you no, because the task was already gone. Now we made it so that even if the task is already gone, has been reaped, you still can get a peer pidfd to it, like you can get a handle on a essentially process that is gone. And the neat thing is that combine this together with the exit information stuff. So you establish a connection to an AF Unix socket, you call connect, you register a specific process with pidfs. That process now exits. pidfs will store the exit information, and then later on you can hand out a pidfd and read the exit status of the connector, and you still have of the connecting process, and you still have a stable handle on that process, which is extremely. The thing is, from a kernel level perspective, all of this looks fairly innocent and not that interesting, but if you look up on the higher level, it becomes very interesting. For example, this is a classic dbus problem, right? So if you have a dbus client that doesn't connect, that is gone by the time the message, for example, gets sent to you, or has been reaped, you can't actually get a connection to it, a pidfd for it anymore, and you can't securely authenticate it. That is now all solved. You can do this now. So this is important for Polkit, for example, too, if you want to securely authenticate clients on your machine. And Luca, for example, has been running around low-level Userspace and stuffed this into Polkit, and I think dbus has dbus broker has support for this as well now. So all of this infrastructure relies on the kernel patches for this, which is pretty cool. And we also extended the concept to threads now, which has been a long-standing request. So pidfds usually only work, okay, thread group leader and threads, is that a common concept? Okay, so usually if you have if you have a single process, then thread group leader and thread is the same thing. But if you have actually threads, you will have a thread group leader and you will have individual threads. And the thread group leader has a specific PID, and all of the individual threads have separate PIDs as well. It's called the TID. It's a massively fucked up concept. I cannot tell you how fucked up this is, but it's really broken in a lot of ways, like threading on Linux. I'll get into this a little bit because I think it's actually interesting. But basically, you couldn't create a pidfd for a single thread. You could only do it for the thread group leader, which we originally did because it wasn't clear what the semantics were supposed to look like if you allowed it for a single thread. So here's how thread groups behave. Let's say you have some user space that doesn't actually know how thread groups work and doesn't know what it's doing, and for example creates a non-empty thread group and then has the thread group leader exit. What happens? Does the kernel reap it or allow you to reap it? The kernel doesn't allow you to reap it. The kernel will basically pin the thread group leader until all the other threads in the thread group are gone. But this behavior isn't the same for the individual threads. The individual threads will just go away, but the thread group leader will stay around. And now we come to a really nasty word on Linux, which is like multi-threaded exec. That all ties into pidfd, believe me. Let's say you have a non-empty thread group and a thread in that thread group execs. What happens? Huh? Yeah, all the threads. He said all the threads go away, which is correct. Like there is a function in Linux kernel that is cursed beyond words, which is called dthread, and what it essentially does, it like kills all of the other threads and then replaces. It's hard to explain, but it kills all the other threads, and the thread group leader has a specific struct PID. Like each individual thread has a separate struct PID, and the thread group leader has a struct PID as well. The struct PID I just mentioned earlier, pidfd's pin. And what happens then, that struct PID is also the anchor with respect to the thread group leader's PID number. And what that happens if a subthread execs is it assumes the old thread group's leader struct PID. Like the kernel literally changes the PID of a process to be of one of the single threads to be the thread group leader's PIDs. Like it switches out the PID number underneath you. So multi-threaded exec is like really weird. So for example, what happens, let's say the thread group leader exits early and you get a notification on the pidfd, hey, this thing has exited now. But then later on, 2 hours later, one of the subthreads, because the thread group leader is pinned, one of the subthreads decides, I want to exec now. What happens is that suddenly the thread group leader struct PID like gets resurrected. It literally becomes alive again. And if you listen on that pidfd, you would get a notification again that this thing is now alive again, because like the individual, like the single thread, has assumed this thread group leader PID. Like a zombie process essentially that came back to life. So it's really cursed because it means if you put this in a poll loop and it happens to be before that other process actually exec, you get an exit notification on the thread group leader. But if you do it afterwards and the subthread has exec and assumes the struct PID again, you suddenly don't get an exit notification because the thing is alive again. So we had to clarify the semantics, and now you don't get exit information on the thread group leader until all of the subthreads have actually exited. But there is a bunch of warts in that area, multi-threaded exec. It's really a cursed part of Linux, and why threads are just terrible. Ideally, we could get rid of this thread group leader concept in general, but it's probably not possible. At least I don't see a way without regressing user space quite massively or changing the model how threads work in user space. And yes, that is something that I just recently did, which I kind of like. For a long time, I wanted to. Do you remember the discussion years back people had about process tags? They wanted to like slap tags on processes so that you could mark them or whatever and so on. And people were opposed to this for valid reasons. But with pidfds we can easily do this. Like one of the first things that I did, I added support for supported X-adders, which means you now can set trusted X-adders on pidfds. Trusted X-adders require privileges. This is why I chose them as an initial concept. Like if you're privileged in the initial namespace, you can mark specific pidfds with a trusted X-adder that only other capable processes can actually remove or retrieve. And it works quite fine. I think this is especially useful for systemd on the host to mark certain processes with certain properties. What I want to explore long term, it's so many hours in a day, and I didn't get around to this at all, but what I would like to explore is the ability to actually have a way to inherit such X-adders across processes. Not trusted necessarily, we could just define our own X-adder namespace for that, but then you can have inheritable properties for processes quite easy, and it's selective, right? It's not something like it's put another way. It's only a burden on any other on the users of pidfds themselves. Like it's not a generic thing that anyone else has to care about. It's literally only if you use pidfds that you come in contact with this, in contrast to process tags, which would be a generic concept, and it's fairly easy to implement. It was fairly easy to implement. Yeah, that if you allow us to do unprivileged, because like currently it's privileged, as I said, then it becomes a bit more tricky because then you also need to account for that you don't get too many X-adders, right? If I just use user X-adders, I think on cgroupfs it's limited to, I don't know, 64 or 500, some memory amount of memory that you get to do X-adders, and we would have to do something like that as well, so that you can't just slap random X-adders on a pidfd and then consume a bunch of memory. But in principle, it's this is a very doable concept. Yeah, and I think that's it. There's actually a bit more stuff, but if I go over that now, we won't have time for questions, and I really like for people to ask questions and comments.
We have a bit more time, but yes, if there are questions, we can take questions. Any question?
Insults.
Yes.
About the pidfd extended attributes,
yeah.
Is it planned or is it already implemented to be able to add your own user extended attributes?
It's not something that I have an immediate use case for. If people really want this, then yes, but then we have the same problem with cgroupfs, right? As I mentioned before, you need some way to limit the amounts of X-adders that you can actually put on a specific pidfd. And yeah, I think one of the most difficult parts of this to get right will be inheritance rules, because that's what you probably want, right? If you mark a specific process of having a specific security attribute or whatever, you probably want to make sure that under some circumstances it's also inherited to children that it forks. Then you also need to think about what does it mean when it execs, right? Like, is it inherited across exec or not? When do you need to strip it? That would be, I think, a lot more involved conversation to have, because then also you need to have, like, security modules need to have a say. I mean, you already have a say, right? Because it goes through the usual security hooks, you can already prevent this from happening. But inheritance across exec and so on is probably a bit of a gnarly problem. And I tried to make people more aware of multi-threaded exec horrors that exist. Really terrible.
Okay, and other question. So what cannot we do right now with pidfd that we can do with just PID?
I think the biggest problem is any system call that currently just takes a PID that probably we can't use. Like I saw some people that have suggested just overloading for example. Originally, I had intended to introduce a new system call to wait on pidfds, which was called pidfd wait, and then it was like, no, we're not going to use a separate system call for this. Just like add a new, you have what do you have? Pid, ptgid or whatever, like these qualifiers for the way that these system calls. So we added a pidfd and we overloaded the first argument. So it doesn't refer to a PID anymore, just it also can refer to a pidfd. And some people have suggested that we could do this for a lot of other system calls that also take flags. I find that kind of ugly, to be honest. What we've seen in recent years is, for example, process release, all of these new APIs that get added, that instead of a pidfd, instead of a PID, they take a pidfd, and this has become especially feasible because, for example, this is one thing I forgot. Allocating a file descriptor is obviously more expensive than just passing a plain PID number. So if you wanted to operate on your own process, you would have to call pidfd open to create a pidfd for your own process and then stuff that into the relevant system call, like process release or process advise or whatever it's called. And we now have sentinels, which are called pidfd self and pidfd thread groups, pidfd thread self and pidfd thread group, I think. This is just like at fd cwd, it just refers to your current process and thread group, which makes this a lot more feasible. And I think so in the future there will be nothing that we can't do with PIDs, with pidfds.
So I have two questions.
Yes.
One is regarding handles. Is there one file system instance, pidfs instance, globally?
Yep.
So all namespace is one instance, so it's unique. Okay. And then the other question, the tags are obvious use case, could be somehow even exposed on systemd. I mean, for examples. Any other use case in mind that you have?
It was really designed with systemd in mind. I don't know, you could have one thing. You could, for example, do what then you need inheritance for that. I think you could mark a specific, like for example, some people insist on something not being a container, something being a container which is not a, which doesn't use a PID namespace. Whereas always advocated for the fact that I think the PID namespace kind of makes sense because it creates a new world, and then it's very easy to define what a container is because you have a PID1 in that thing. But some people don't use that. Like you could, for example, set an xadder on the pidfd and use that as a marker for this is a new container. But the thing is, then you need it to be inheritable, because like if something forks, they won't inherit the xadder currently. But if you have an inheritable xadder, then you suddenly have a process tree, and they all are marked as belonging to the same container, for example, or whatever concept you want. Container is just a vessel here. You could define your own, whatever you want it to be. You could just mark a group of processes as having a certain property, and that can be quite arbitrary, especially if you, I don't know,
So maybe one more follow-up. At some point, David Howells or somebody posted a patch set regarding sort of implementing this container type for a kernel. This could maybe reuse some of that and implement the inheritance, and you know what I mean, I guess.
So yeah, I will be very surprised if we ever get an actual kernel concept. I think that will be, let's put it like this, it's not a battle I want to fight, and I would argue that I'm probably in a very good position to fight that battle, but it's not that interesting to me anymore, especially if something that I didn't talk about this time, but which I could also talked about just for the 6.18 merge window just now in the batch of pull requests that I sent, and it was merged on Monday. I there was also so the network namespace and the mount namespace both have a concept of a unique identifier. So in the network namespace, it's called the netns cookie. So each network namespace has a unique cookie. You can retrieve it via a socket option. Why it's a socket option, I don't know. And you can get this unique identifier. And we also added the same concept, Joseph and I, to the mount namespace so that you can get a unique identifier for the mount namespace, like a cookie that is not recyclable for the lifetime of the system. 64-bit identifier, ever increasing. And we extended this concept to all of the other namespace types now. So for example, if you wanted to define your container and you know the set of namespaces, each namespace now is a unique identifier that you can consistently and non-recyclable refer to as the container. So it's very easy to just uniquely define like a tag or a handle on what a container actually is. And then in follow-up kernels, we want to have an API that you can iterate through all the namespaces without ever having to touch proc.
So we don't need this high-level concept and have another endless discussion. There is a way, essentially.
Yes, I mean, there is something to be said for having. I think if you could have redone it, you would have probably wanted like a proper in-kernel container object, because it would make a lot of things nicer. Like, but we have so many moving parts now that it's. I don't know how feasible it is anymore, and we've solved some of the really annoying problems. Like, for example, one of the things that David Howell's patchheads really wanted to do, if I remember correctly, it wanted to have an in-kernel object so that it can shove mounts into the container. It could just say mount into something, and then create processes in that specific container. With the new mount API in place, we can do this. Like, we can have a specific FD that we hand to a container and inject mounts into the container nicely. So a lot of the original friction is gone. The price that we pay, unfortunately, and you can see in every talk that, for example, Leonard gives about low-level container runtimes, is that there's no way to sugarcoat it. It's a lot of complexity, right? It's not a trivial task to implement your own container runtime, even though everybody apparently does. Like, I don't know how many we have, but over the years we have like 10 container runtimes, and every few years somebody implements a new container runtime and then gets to repeat the same mistakes we all did for the last 10 years, and we get to relive all of the CVEs again. Ptrace issues, I don't know, everything. So there's a lot of security sensitive stuff that you can do. There's a lot of foot guns, and that is unfortunate. It would be easier if you had an in-kernel object, an opinionated in-kernel object, where all of the issues are taken away. For example, if you could redo it, you probably wouldn't do the user namespace the way that we did it, where you have mappings between UIDs and GIDs, because I think the only reason we have maybe ID map mounts are useful independent of the user namespace, because I implemented them in such a way that you can use them on the host. Like, it's just useful if, for example, you want to create a mount where you map UIDs to a different range of UIDs, which is, for example, very nice if you want to carry your home directory between different machines and want to make sure that the UIDs and GIDs match. So it's useful for that. But one of the motivating factors was obviously that we have this insane mapping between UIDs and GIDs that nobody really wraps their head around, or at least spends a year to actually figure out how to do this correctly. And then it's still limiting, because you can only have a limited amount of containers if you want to have a full range of them. And still some programs won't run in the container if they use very high UIDs and GIDs. So I think we have paid a tremendous price for the flexibility that we have. On the other hand, if we had an kernel container object, we'd have missed out on a lot of stuff like portable services, a lot of the default sandboxing that we have, like the pid namespacing, the user namespacing, the mount namespacing stuff that each systemd service has. Like, on a system hardening level, it's great, because like if you know what you're doing, and if you have a very good low-level user space project by systemd run by actually opinionated and people that have an idea of what they're doing, you end up with like nice service isolation that I think. On the other hand, if you just like want to do a container, you suddenly end up with a bunch of duct tape, right? And really weird issues. So.
Right. That is all the time we have. So thank you, Christian.